Okay, so like I said, today we're going to go through the last three methods that we're going to look at for system ID. And then in Thursday, we're going to, at the very least, we're going to look at a short list of other methods out there. And then we might do a review as well, we might not. Today we're going to look at what's known as the sparse identification of nonlinear dynamics, or the SINDI method. We'll then look at a global local method. And then we'll look at, lastly, a method based on using frequency energy plots to update models. Okay, so the sparse identification of nonlinear dynamics, or the SINDI method, is a very popular method in general, and there's been many extensions of this method created over the last decade or so, maybe a little bit less than a decade. Our entire discussion is going to be based on section 7.3 in this reference shown here. It's a book that they wrote. We're going to use their SINDI algorithm, and we'll look at just one example from their book. And you can find tons of papers on this in the literature. So the whole idea is the fact that trying to identify both the mathematical structure and the underlying parameter values simultaneously or at the same time can be very challenging, because there are many different combinations of mathematical structures that you could consider in trying to do that parameter optimization. So the SINDI algorithm is a method that tries to bypass that challenge by searching through all possible model structures and then leveraging the fact that the dynamics of many dynamical systems, and here we're talking about systems like x dot is equal to some function f of x, where f is a vector and x dot and x are both vectors, have some kind of dynamics f that will only have a few active nonlinear terms in the space of all possible functions or terms that could exist. So generally we're thinking that most of the systems we've studied have only a few linear stiffnesses and a few nonlinear stiffnesses or damping terms that are coupling the degrees of freedom. And you could imagine that it could actually be, there could be an infinite number of terms that could be, but pretty much everything we've seen has only had a few of these. So this dynamics is relatively sparse compared to what it could be. Okay, so the idea then is that we seek to approximate the dynamics f using a generalized linear model, where we'll say that this is some summation starting from k equals 1 all the way up to some value p of a function theta sub k, function of x, multiplied by some vector of constants c sub k, which we can then write as capital theta, which is now a matrix, which is still a function of x, multiplied by the vector c, where we would have as few non-zero terms in that vector c as possible, indicating that that c vector should be sparse. So SINDI identifies this type of model by using sparse regression that penalizes the number of terms in the dynamics. And as a result, this approach tends to scale well to large problems. So the first step in this method is to assemble a data matrix. So the assumption is that you have some kind of time series that you've measured. It could be transient or it could be forced response. But you have that data ready. We then want to assemble a data matrix just by collecting all of those terms. And so our data matrix big X will be equal to the collection X at T1, X at T2, and then all the way up to X at T sub m. And that guy is then transposed, which is then equal to the matrix, first degree of freedom at T1, all the way up to that first degree of freedom, or first state variable at Tm, up to, let's say, x sub n at T1, and then x sub n at Tm. So that's our data matrix, and then we also build one for the time derivatives of those states, which we'll just write as x dot at T1 up to x dot at T sub m. So here we're doing this for continuous time systems with the assumption that there's obviously some sampling going on here, and we're not measuring for infinite time. You could formulate the Cindy approach for a discrete time system. Like if you think about when we did maps and we were looking at like xk plus 1 is equal to some function of x sub k, you could formulate Cindy to work with those kinds of systems as well. We are considering continuous time in this application. Okay, so the second thing we do once we've built this data matrix is that we want to construct a library of candidate nonlinear functions, and we're going to call that's our big theta, which is now a function of big X. And in this case, this matrix will be capital theta evaluated X equal to, typically you start off with a vector of just ones, and we can say big X squared up to big X raised to the D power, maybe the sine of big X, the cosine of big X, and then whatever else you want to include in this library of functions. And so here, this xd is a matrix with column vectors of all possible time series to the dth degree polynomials in that state x, meaning that you can have x1 squared times x2 cubed, and that would give you d equals 5. That would still be considered 1. And so in general, this library of candidate function is really only limited by your imagination. Although I would argue that knowing something about the physics of the system, having some idea would allow you to constrain this library rather than including every possible function ever. All right. But if you wanted to, you could include as many things as you want, whether or not they actually make sense or not. And typically, the Cindy algorithm will end up rejecting things that don't work. Okay, so third, what we want to then do is express the dynamical system in terms of those data matrices. So that means that we'll have here big X dot is equal to that big theta evaluated at this big X, so our library of candidate functions, times a matrix of values or parameters. So each column in this capital C matrix is a vector of these Cs, and it's a vector of coefficients determining the active terms that are in the kth row. And we'll see a little bit when we look at their example. So the goal is to produce a model that has an accurate fit using equation 35 with as few terms as possible in that capital C matrix. And we end up doing that using an L1 regularized sparse regression, which means that these C sub k vectors should be equal to the argmin with respect to C prime sub k of the norm x dot k minus theta x times You see k prime, that's the norm 2, plus lambda here multiplied by the magnitude of you see k prime, and 1 there, where x dot sub k is the kth column of that x dot matrix, and then lambda is a sparsity promoting knob, meaning that we get to choose what lambda is, and then if one of our parameters has a value less than that lambda, we will typically reject it, or the SIND will reject it. There are several different methods for implementing this sparse regression. The book uses the sequentially thresholded least squares method, which is what we would just use as well. This is the function from that book. Effectively, they just loop through. They start off by doing the first regression. They check to see which one of those are small indices or just small. They then set those to 0, basically rejecting terms that are not contributing to the response or only weakly contributing. And then they loop through this several times to try and find the minimum number of parameters and functions that are needed to reproduce the response. Okay, and so after you build this model and you know what these parameters are, you can then go ahead and use that to build the mathematical model, in which case we can reproduce the kth state variable, x dot sub k here, and these are lowercase x's, is equal to now big theta. In this case, it's now evaluated at lowercase x and multiplied by c k. So the key thing here is that equation 37 is a symbolic equation. It's not a data matrix like we were dealing with before. What we've now done is identified the parameters in that C matrix, which tells us which functions in theta to keep, and we're now inserting an analytical variable x into that, or all of the different state variables into that library of candidate functions. So effectively what we now have are the equations of motion, in this case, as reproduced by the SIND algorithm. Okay, we're going to just take a look at the example that they provide in their book. One thing I will say is that people have extended this method a lot. They've started implementing in machine learning approaches, and there's still work to be done. I think some issues they have are when there's a lot of noise in the measurements. There's been some work when you don't exactly have the right coordinate system in your measurements versus what the actual coordinate system, like the lowest level coordinate system you could use to represent the system. But it's an ongoing area of work, and if using the basic SIND doesn't work in your application, there's probably an extension somewhere that will at least get you part of the way to where you're trying to go. Okay, so in the book, they just cover the Lorentz system. Lorentz system is a simplified model for atmospheric convection. It's named after the famous nonlinear dynamicist Edward Lorenz, who was one of the originators of chaos. In fact, the Lorentz system, this set of equations that I'll write in a moment, was the first time somebody observed a quasi-periodic response, and then this then led to them identifying as a chaotic behavior and then being dependent on initial conditions. And if you've ever heard of the butterfly effect, that's from this system. This research is the originator of that statement. And in fact, Lorenz's presentation or paper that he wrote on this, the title is something like, does the flap of a butterfly's wing in Brazil cause a tornado in Texas? It's something along those lines, not exactly that, but that's what his original presentation was. All right, so it's a system of three equations. X dot is equal to sigma times the value x or y minus x. Then y dot is equal to x times the quantity rho minus z minus y. And then the last state equation is z dot is equal to xy minus beta times z. So here the parameters are sigma, rho, and beta, and then the state variables are x, y, z. One thing I will say that this is a 3-state variable system. You can only have chaos in systems that have 3 or more state variables. So something like the Duffing oscillator will never, the unforced Duffing oscillator will never exhibit a chaotic response. The forced Duffing oscillator, in that case, time becomes a state variable. And in that case, you can get a chaotic response. And that's why when you did like the phase space for the Duffing oscillator, the forced Duffing oscillator, we extended that into a third dimension of time. Okay, so I'm just going to show you their figure from their paper. They basically do a simulation of this. That's what's shown on the top left there. They choose the following candidate library. You can probably see those, look at the notes. They choose these functions. They then do their sparse regression, and what they find is, if you look at the Cassie matrix, they have these 2 blue terms, these 3 red terms, and 2 green terms, and those are the terms that survive and are kept out of all of the possible terms that could exist in this model. And it looks like they go up to the 5th order polynomial. And then you can see there's the result of their identified system, and beneath that you can see what the Cassies are. The parameters are shown beneath that in the code. I'll zoom up a little bit. And you can see that they're getting relatively close to the actual parameters that you find that they used in this model. Okay. In the book, they do apply this to another example, which is vortex shedding. In that, they apply the POD to it to extract some proper orthogonal modes, and then apply Cindy to those modes as well. That's another example that people have done. And so what I will say about that is that the Cindy method is modular, meaning you can do this. You can do the model reduction first, and then apply Cindy to that. So you could, for example, do the wavelet bounded EMD, and then apply Cindy to identify oscillators for each of the IMFs if you wanted. I don't think anybody's ever done that, but you could. And then after that, you could then think of how can you do an inverse of that wavelet transform, wavelet bounded EMD to go back to the real system. It's very modular in that sense. Extremely popular method. A lot of people have done research on it. It's very simple to implement, which also means that it's not necessarily going to work for very complicated systems or very noisy or real measurements. Particularly, I haven't surveyed the literature super extensively, but I could imagine that this would be struggle on data that's measured in like real operating conditions out in the field. I could imagine that this would struggle with that. That is for you guys to discover. All right, so the second case or second method we're going to look at is a global local approach to nonlinear system identification. Our study of this is going to be based on these 2 papers shown here, and this kind of really pulls together everything that we've talked to in terms of FEPs, EMD, empirical slow flows, etc. It really brings all of that together into one tool to try and identify the underlying dynamics. And it relies directly on processing of measured time series. And so the central assumption here is that the dynamics can be decomposed. And in fact, before I do this, were there any questions about Cindy? Before we move on, I forgot to ask.
I wanted to ask about that L1 regularization.
Sure.
So this L1 is going to eliminate the term right away, right? Because I think L2 would decrease the effect of that right?
Yeah, I have not studied it, to be honest. So I can't comment specifically on what each term is doing in this, but what I can tell you just from experience through this approach is when you go through it, it does this regression here. And what it then does is it asks what terms are small, and then it sequentially will set those to 0. And it's an implementation of this condition here. and you can check the book for this, and more importantly, you can check their papers, which are readily available out there. And Steve Brunton and Nathan Kutz have tons of YouTube videos on this as well, where they talk about this stuff. I'm not so much an expert on this, so I can't exactly answer what the effect of each of these terms are in this optimization, other than what they say. Are there any other questions? All right. In that case, let's go back to this. So we're going back to this global-local approach. I mentioned that this synthesizes pretty much everything, a lot of the topics we've been talking about, and performs a system identification method. And so the central assumption is that the dynamics can be decomposed in terms of slowly modulated fast oscillations. Which is kind of the core message of what we've been doing this entire class. With multiple scales, where we said there was a fast oscillation with a slowly varying amplitude. We then did CXA, where we had the same assumption. When we did wavelet bounded EMD, when we started looking at these nonlinear resonances, we encountered this idea of a slowly varying amplitude multiplied by some fast oscillation. So in general, this is kind of not a very hard assumption to satisfy. Of course, if your system is linear, then this assumption is not true, but there are tons of linear techniques to use, and you wouldn't need to apply something this sophisticated anyway. Like I said, this is a reasonable assumption for non-chaotic data, meaning that you have a regular response that you've measured. If it's a non-regular response, then you can have issues with this method. All right, so we're going to go through just kind of the basic steps, and everything in black is what they wrote in the original papers. The things in blue here are kind of my comments on what I would do now, because when were these written? Like 13 years ago, these two papers were written. Before the wavelet bounded EMD existed, before some other tools that we now know about existed. And so I think the blue is just kind of things that I would change. So the first thing to do is that you're going to measure time series from a number of sensors throughout the system under a transient excitation, so like a hit from a hammer. And then you're going to perform EMD, and we would now use the wavelet bounded EMD for this. We would not use the regular EMD to extract IMFs at each sensing location. So then this next step, you would then use the Hilbert transform to compute the instantaneous frequencies and instantaneous amplitudes, and you compare those with the wavelet spectrum of the measured time series. That's just a good practice in general to make sure your IMFs actually make sense and represent what you're looking for, whether you're using EMD or the wavelet bounded EMD. And then in the original paper, they say based on that comparison, you're going to determine what are the dominant IMFs. So what they mean here is that when you just apply the basic EMD, you tend to end up with a set of IMFs that are physically meaningful, that represents some component that you can see in the wavelet transform, and then you end up with another set or subset of the total set that are spurious and don't really have any physical meaning, and so you would tend to reject those when you apply the regular EMD. When you use wavelet bounded EMD, you're choosing what you're trying to extract, and so you don't end up with these spurious IMFs that you need to reject and exclude, because it's directly extracting these dominant IMFs. So you would skip that. You wouldn't need to make a decision on what to keep and what not to keep, because you just keep all the IMFs. So from there, we're going to relate the slow components of the IMFs to the slow flow dynamics. This is exactly what we were doing when we looked at nonlinear resonances and tried to use the wavelet bounded EMD to identify that. The same procedure. Again, this provides this local identification of the behavior, including these nonlinear resonances, and as well as nonlinear modal interactions. From there, you're going to use the dominant IMFs to reconstruct the time series and depict that in a frequency energy plot. The assumption that we make here is that there's weak dissipation, and this allows us to extract a portion of the frequency energy plot of the dynamics of the system under investigation. So let's kind of unwrap this a bit. When we talked about nonlinear normal modes in a frequency energy plot, we were typically looking at Hamiltonian systems without any damping or any forcing in it. So the assumption here, and this tends to work as well, is that when you have weak dissipation or weak damping, the frequency energy plot of the actual system is just a slightly perturbed version of the Hamiltonian FEP. So that means that the FEP of the damped system is a little bit different than the FEP of the undamped system, which is valid and tends to be true because most structures are weakly damped to begin with anyway. Typically you have to specifically implement damping to make these things high damped rather than weakly damped or strongly damped. Okay, and so you can compute the energy of the system with the IMFs, or if you have a model of the system that you trust and you think really reproduces this, then there are other techniques that compute the energy as well. But the key thing here is that just directly analyzing the time series and producing these IMFs, you can then produce the underlying frequency energy plot, which then tells you how the modes of the structure evolve over energy, which basically is equivalent to understanding what the system is doing, knowing the dynamics of the system. And so in this case, no a priori model is assumed for this reconstruction. If you wanted to, you could use a model to reconstruct the energy, but you don't have to. And this is where you get this non-parametric global component. Global meaning that it represents the entire dynamics, not just the dynamics of a particular response that you've measured or a particular set of initial conditions. It represents the global response over many different initial conditions. And so one thing I think I'll add here is that you don't necessarily do this for only one response or one set of measurements. You can do this for multiple sets of measurements and then map out how the FEP changes. And I have a picture that we'll look at in a moment where I can talk about that. Okay, so step 4 is once you have a nonlinear transition in that FEP, you can then define a parametric reduced order slow flow model, and then you identify the parameters for that model. This then gives you a local slow flow model for that dynamics. This is what we would call the parametric local aspect of the nonlinear system identification. Okay, so step 5, we would now vary that excitation or initial conditions and consider different transitions in that FEP over different frequency energy ranges, and then use that to construct portions of the FEP of the system together with that associated slow flow models. And then at the end of all of this, the final outcome are a frequency energy plot that characterizes the global dynamics, depicting different possible coexisting solutions, their bifurcations over a wide range of frequency and energies of interest. And then on top of that, you also have some type of local slow flow models that will describe how nonlinear transitions occur in the FEP, as well as how different modes will interact with each other and what are the conditions for those. Okay, so we're going to go through the global aspects of this, and then I have a picture on the next page, and then we'll talk about the local aspects. We'll take a look at a summary of this method, and then we'll see, I think, 2 examples of how it works. Okay, so starting the global aspect, we're now looking at how to reconstruct a frequency energy plot. And so we can compute the energy of the system using the dominant IMFs. In this case, we're going to say C sub k raised to the m, and that m is not power, it's an index here. So this is the mth IMF at the kth degree of freedom. And the corresponding energy is going to be E sub km of t equal to the 1/2 power times the quantity, the quantity C sub k m dot, in this case, of t. So this is either the time derivative of your IMF, or it could be the equivalent IMF for the velocity signal. So that term squared plus the frequency omega sub k m t times c k m t, that quantity squared. And here this first term is like a kinetic energy. and that second term is the equivalent potential energy. So that gives you the energy for the mth component at the kth degree of freedom. And then assuming you know the mass distribution, which is typically relatively easy to compute and know, then the total mechanical energy becomes, we'll say E sub tot of T is equal to eta times the summation of K equals 1 to lowercase n, and summation from M equals 1 to big N. So there are lowercase n degrees of freedom and big N components for each of those degrees of freedom. Then the mass of the coordinate K, M sub K, times the energy at EKM of T. And here, this eta is a correction factor that's used to match the exact initial conditions of the damp transition with the approximate initial conditions satisfied by the IMFs. And for a linear system, you'll find that eta is equal to 1, and for a nonlinear system, it will be greater than 1. I personally have not computed this eta before, but I suspect that it would not be very difficult to compute with matching these initial conditions. Okay, so now that we have this total energy, we can then plot the IMFs as a function of that energy, and that is what is shown right here. Oh, yeah.
So is that M that's next to the E, is it as a mass, or is it also an index?
I think that is actually the mass, but that's a good question. It has to be the mass because it has a subscript K, and if it was an index, it wouldn't make sense to have a subscript. But I agree with you, this is a confusing.
So I'm just going to use M
Yeah.
cap, so no.
So let's just make it here. M sub K is the mass at kth DOF. However, that has either been measured or estimated using some model technique. Let's just be clear of what that is. You're right, that is actually conflicting and confusing. That's fair. I'll give you guys a moment. It looks like everyone is caught up. All right, so this is what that ends up looking like. This is, I think, the LONES vibro impact system. We'll see an example of it in a moment. So on the left, we'll kind of talk about this in the light gray lines. That is the analytical FEP or the model FEP for this particular system. The colored lines are the instantaneous frequencies of IMFs. With the blue ones, I think, being for the NES, the red ones being for the LO. Anyway, you can see how the lines here line directly up with portions of that FEP. On the right is the wavelet transforms of the IMFs, and this comes from two different responses shown here, two different simulations, I should say. Anyway, you can see again how the IMFs overlap with this FEP, which is how you can use this wavelet FEP as a way to characterize the behavior. Okay. Which I think in one of the examples of the wavelet bound EMD, we showed how this maps on top of the FEP. So the idea, of course, is that you wouldn't know the analytical FEP in practice because you don't know the system. You don't know what the nonlinearity is or the behavior of the system. And you'd want to use these kinds of plots as a way to interpret and understand and figure out what is going on and the different types of transitions. And here there's only two responses or two measurement cases used to reconstruct this. And so you could imagine doing additional tests or simulations and then using that to try and understand and construct this FEP. Okay, so the local aspect focuses on building these slow flow models, which is what we've talked about a lot here throughout this course. And so the focus is on creating what we call a nonlinear interaction model, or a NIM, and that is in terms of what we call intrinsic modal oscillators, or IMOs. And an IMO is an equivalent linear oscillator that can reproduce that measured time series over different time scales. And we'll kind of go through what this looks like. So we're going to typically express an IMO or IMOs as a set of linear damped oscillators with nonlinear interaction models as their forcing functions. So for the kth degree of freedom, x sub k of t, we would then express that in terms of n fast frequencies, or fast frequency components corresponding to n IMFs. And then we define an IMO corresponding to the mth component, which has a fast frequency omega sub m, in the form of, in this case, we'd say x double dot sub k m of t plus 2 zeta sub k m times omega sub m times x dot sub k m of t plus omega m squared times x k m of t is equal to some forcing function f sub k m of t, and then here this m is varying from 1 up to big N. That's all of the fast frequency components, and then of course the k varies from 1 up to lowercase n, and that is the number of degrees of freedom. And here we've assumed that the zeta, or this linearized damping ratio, is constant, and we're also assuming that the fast frequency is constant as well. So with the energy, we were looking at the temporal frequency computed from the IMF. Here we're looking at just an assumed constant fast frequency. And then lastly, this f of t term, that describes our nonlinear modal interaction term of the mth component, and for that degree of freedom x sub k. So the idea then is that we can express that forcing term in terms of a slow-fast partitions of all of the frequency components. So building on this idea that we can produce, we'll have some oscillation that's a fast frequency multiplied by a slow amplitude. We're now going to do the same thing here. In that case, we will expand this to be the real part of the quantity capital lambda sub k, and here m is 1. This is our slowly varying amplitude multiplied by j times omega 1 t plus dot 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 plus lambda sub k m of t times e to the j omega m of t plus dot 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 plus lambda k big N of t times e to the j omega n t. And so here we're simply breaking it up into a fast oscillation, the e to the j omega t, multiplied by a slow amplitude, that lambda term. And then we're saying that there's a term for every single component or mode that occurs at that degree of freedom. And I've left off the last portion of that, so we'll add this in here. So this lambda represents the slow amplitude, or modulation of the fast frequency. Slow amplitude / slow modulation of the fast frequency. All right, so due to the linear structure of the IMO, the only term in that forcing function that is going to produce an order 1 dynamic response is the one that has the same fast frequency as the IMO itself. So you can think back to when we were looking for secular terms in the method of multiple scales. We were looking for terms that had the same fast frequency as the oscillator itself. I come back up here, our frequency, our linear frequency is omega m squared. So the only forcing term that's going to give a large response is the one that has the same forcing frequency. And so as a result, we can then simplify this down to, and I thought I left more of this in here, but it will be x double dot km plus, we'll drop the time portion, time plus 2 zeta sub km times omega m x dot km plus omega m squared x sub km. And then this is approximately equal to the real value of lambda sub km. That's a function of time. We'll leave that in there, times e to the j omega mt. And that is therefore our reduced order model for this IMO. And again here, m is equal to 1 up to big N, k is equal to 1 up to little n, which is the number of degrees of freedom. Okay, I'm going to skip some steps, but effectively through the equivalence of the complexification averaging and empirical slow flow models that we've seen previously, we can express this lambda term as the following. We can express it as 2 times the quantity d over dt times the quantity j omega m times a hat. And here I'm going to use the hat to represent the Hilbert transformed amplitude of the corresponding IMF. Km t times e to the j theta hat km. And so that's the phase of the IMF that's been extracted using the Hilbert transform, plus j times zeta km omega m squared times a hat km t times e to the j theta hat km t. Once you have these lambdas, you can then study the effective forcing function, and that then allows you to determine the different types of modal interactions that can occur, that are occurring in the response. Okay, I will give you guys a moment to catch up. And then we'll just go through a brief summary of this method, and then we'll take a look at an example. We'll take a look at 2 examples. There won't be any code for these examples, unfortunately, but I do provide some references. All right, so just to summarize this method, we start off by doing measurements, particularly looking for time series and doing transient response measurements. We then do a time frequency analysis, just looking at what the components are. From there, we do the EMD analysis, extracting out different IMFs. In today's time, you would probably use the wavelet-bounded EMD to do this instead of just the plain EMD, therefore determining what the dominant components are directly. You then do this analytical equivalence with the empirical and analytical slow flow models. You can produce one using CXA, which gives you analytical slow flow, and then you produce one using the empirical mode decomposition to produce this empirical slow flow. You then build a nonlinear interaction model, which is exactly what we just did with these IMOs, as shown there. And then lastly, we will do a verification and validation of this and show that we can reconstruct the response using these types of oscillators. All right, so just a quick example looking at this Vibro Impact NES. This comes from one of the two papers. I think they actually both use these results, the papers I cited at the beginning of this section. The schematic is shown there. In addition to what's shown in the schematic, they also include viscous damping. The equation of motion is shown to the right there. You can see they have a viscous damping term in the second equation of motion, which is not included in the schematic, but you could add that yourself. Shown on the left here are two displacement responses and then their relative displacement shown there. They show the time of that last vibro impacting occur. Using the IMFs, they then construct and reproduce the frequency energy plot. That's what's shown on the right here. The colored solid lines are from the actual analytical FEP that they computed using the Hamiltonian system. And then in the background there, that shaded portion is the wavelet transform of the IMFs. From there, they went ahead and built this nonlinear interaction models, exactly like we talked about before. And here you can see what this kind of forcing function looks like, or what that slow amplitude looks like in general, with there being in the beginning, well, it decays very rapidly in the beginning, and then for the NES, it starts to decay almost linearly. And then on the right, they've been able to take these IMOs, that's in red, and reconstruct the behavior of the IMFs, as shown here. Okay. We're going to take a look at another example, one applied to a beam. In this case, it's a bolted beam. The reference is from a book shown here. Although I'm the author of this, I didn't actually do any of this work. This is in a book, and I was tasked with writing it, so they put me as the author. However, it was based on work that Mehmet Kurt and Melly Ayrton did prior to me joining this group. So nevertheless, the system they studied is a bolted beam comprised of basically two half beams connected with over a lap joint shown there. And then they also tested a monolithic beam without any joints in it at all. So in this testing, what they did is applied an impact, shown at the location there. Then they measured the response using a laser vibrometer at the grid points shown in red there. Okay, so shown down here is, on the top is a typical force measurement. Beneath that is the typical frequency response for that force. And then below that is the FFT of the velocity response at one of the measured locations. And so you can see that with the monolithic beam, I'm going to circle it right here. You can see a little bit here, but really you can see here and here. The frequencies of this monolithic beam are higher than the frequencies of the bolted beam, and that's pretty typical because a bolted joint is less stiff than a solid member in general. So by introducing these bolted joints, we not only, at least in terms of linear response, we are shifting the natural frequencies to lower regions. And then at higher amplitudes of testing, we're going to introduce a lot of stronger damping due to friction and other effects. All right, so you're going to have to turn the next page on your side, and I'm not necessarily sure I can even do that in a way that will work on the projector. But we'll just do this. So this is a grid of different measurements with each plot lining up with the measurement coordinates, each series of plots. And this is just to demonstrate what the behavior looks like. So this beam was suspended using fishing wire, which is why we get this kind of large oscillator response or very low frequency oscillation. That's due to kind of a pendulum type motion occurring in the beam. All right, let's move on and take a look at the empirical mode decomposition. This is not one I did, and this is not done with the wavelet bounded EMD. This was done using just the standard EMD, and I assume they either used, actually probably they didn't use like masking signals or anything here. This is probably just a basic EMD. And that's why you can see there's kind of considerable mixing in the IMFs based on that wavelet transform. So when I was writing this chapter for this book, We had not yet applied the wavelet-bound EMD to this data, and therefore I ended up just using these results. But after this chapter, after I wrote this, we did apply the wavelet-bound EMD to this, and you can get very clean IMFs using that technique. The results here are not based on that, though. Okay. So again, because of the way they're doing this, they have to choose a subset of dominant IMFs and then show that that subset can reproduce the response shown here. This is exactly what we're doing. Green is the measured, black is the summation of the IMFs that they kept in this analysis. If we move on here, so here's where we're going to look at the logarithm of that slow amplitude, and I'll use that as a way to compare it to a linear modal analysis or a linear damping ratio as shown here. And so these plots that I'm showing right now, these are for the monolithic beam, which you would expect to behave relatively linearly because it's a linear system. And you can see in general that the amplitude, although their filtering, in my opinion, could be better here, but in general you can see that they're relatively straight lines. They don't change over time. Certainly for the second, the third, and the fourth IMO, and then the fifth IMO as well, although there are some effects in the higher ones. This is likely due, these effects that you see here, if we come back up to the IMFs, you can see that, for example, in the sixth mode, there is a mode switching that occurs. There's a mode switching that occurs right here, where we jump from one frequency to another frequency, and probably this component right here should probably be right there. So those effects that you see, in my opinion, having not analyzed this data for like 10 years, those are probably poor IMF issues that we see in these IMOs, like the effects here. This is probably just due to having poorly separated IMFs. And like I said, I did apply the wavelet-bound EMD to this data set, although we never published it anywhere. Okay, so this is now for the nonlinear data. You can see here. So here they no longer align well with the linearized damping curves in the solid black or the dashed black. You can see they are now stronger than that, and this implies that there are some nonlinear effects occurring that changes the rate of dissipation here. These red lines are, what are they? They're the times where the IMO is nearly zero. So the response to the IMO is nearly zero. So in the sixth and the fifth, you can see that, or certainly in the sixth at least, you can see that there's a much steeper dissipation than we saw previously. This is a comparison of the spatial variation of these decay rates. So the logarithming of this slow amplitude for this bolted beam, that red line that crosses across all of these indicates the times where the signals are vanishing due to that damping. And you can see here that in some of these, there are a spatial variation of the damping curves and their behaviors, indicating spatially localized responses. All right, and then you can also plot these as functions of the energy in the system and show that at higher energy levels, the damping is higher and so forth. We won't go too deep into this. If you're interested, I can give you the paper, or I can give you the original paper that the book chapter was based on. All right, so last method we'll talk about relatively briefly is this, just a technique for doing nonlinear model updating using frequency energy plots. So the method was presented in the papers shown there, and the basic idea is that you have a model, you've proposed a model at least, and typically you would propose one based on a frequency analysis of the system. And once you propose the model, you now want to identify the parameters on that. So the basic idea is to optimize those parameters by maximizing the fit between the model frequency energy plot and the measured frequency energy plot. So the basic summary of the procedure is that we're going to start with a transient excitation. That will go into the system. We'll then measure that time series. We'll extract instantaneous frequencies, amplitudes, and energies. We'll then construct an empirical frequency energy plot. From there, we will define a model for the local nonlinearity. We will compute the frequency energy plot for that model and compare that with the empirical frequency energy plot. We'll ask, is there a good match between the two? And of course, based on some tolerance, if there is, then we'll stop. If there isn't, we will update and change the model. And that updating can be done using optimization, or it can be done manually if you wanted. There are several different approaches for that. All right, so we're just going to talk about an example or what that entire paper actually covers, which is the application of that approach to this round-robin benchmark system. So it's a system of two beams with the sensors located at A, B, C, D, etc. It's two beams that are connected by some mysterious element that we don't know. This is a benchmark developed by the community, and it's a simulated system, and you can apply a force at location D. And again, because it's a benchmark, we don't know what that element is. Eventually, they did publish a paper, and so now we do know what it is. But at the time of writing this paper, that wasn't public knowledge, so we didn't know. All right, so basically what we did is that we applied an impulsive force shown like this with some amplitude that we varied and a fixed duration of 1/10,000th of a second. Again, we're applying that at location D, and then we're measuring at A, B, C, D, E, F, G, H. And what I'm showing here is just I'm going to show the displacement, wavelet transform, and F of t of the response at location sensor D. This is for 1 Newton, so very linear. For 1,000 newtons, it's still pretty linear. And then for 2,500 newtons, it starts to become somewhat nonlinear. We went up to 5,000, and then also up to 7,500, and then 10,000 as well, shown on the next page here, just to probe the full range of the nonlinearity. And I think if you go above 10,000, you start to run into computing errors with this. Again, this was like 9 years ago that I did this stuff, so it's been a while. I'll also say that, again, this was simulated, so what they provided to us and to anyone who wanted to do this was a MATLAB.p file, which is basically a .m file, but it's locked, and you can't open it and look inside. So we can't see what's going in, but we can provide it inputs like any other function you would like to run these simulations, but you can't peer inside and understand what's going on in it. So that makes it truly a black box simulation. Okay, so here is a comparison of the FFT for all of those different simulations, just showing how they vary and change. And the little box in the bottom left is just a zoomed in view around here. Just showing how this extra frequency content is introduced and how that second mode changes. And actually it seems to be decreasing in frequency, indicating some type of softening nonlinearity. Okay, so let's talk about it on the next page. And again, I'm taking figures from a paper, so we're missing a lot of the in-between analysis that was done here. One thing that you can compute with this model, so in this case, we know the dimensions of the beam, we know the general material, and so we can build a linear finite element model for this. And that's where these mode shapes come from, is our linear finite element model, not the model that the people who created the benchmark system, not their model, whatever they're using. We wrote our own finite element model and produced that. Based on the observations of that frequency content, we proposed that the model should be some type of one-sided softening nonlinearity, where once the relative displacement between the two beam tips reaches a positive value of xb, then the stiffness suddenly decreases. That was the idea. So here is a frequency energy plot showing in red is the frequency energy plot, or the NNMs computed using the toolbox NNM cont that I've talked about before. And in the background wavelet transform is the actual is what comes from the measurements or the simulations itself. And I forget which response we did this for, probably like the 5,000 or the 7,500. You can read the paper for those details. And this XB is I forget how we computed that, but it relates to the relative displacement and how much energy needs to be in the system in order to achieve this relative displacement, which you could start by looking at, for example, the mode shapes and converting that into an energy and determining how much energy is needed for these things for that relative displacement to be large enough to reach XB. Okay, so once we've identified this model, we can then go ahead and try and reproduce the simulation results. And that's what I'm showing here. What you probably can't see, at least in this very first two plots, is that there is a dashed gray line that sits on top of this black line, and it's unfortunately a very dark gray. But what we're showing here is that at the linear regimes, we're able to reproduce the response, which you would expect to be able to do. If we go higher here, you'll start to see, particularly in the FFT, you can now see that there's another, at least you can see there's a second curve. You can see here that our model is doing reasonably okay for this behavior. In general, looking at the 10,000 Newton response, you can see that the model is at least capturing the overall amplitude or shape and behavior in the time series. And in the wave transform, it's doing an okay job as well. Okay, that concludes what we are going to talk about today.